Hello, and welcome to the first of our 2020 Low Carbon Energy webinar series. I'm Robert Stoner, the Deputy Director of the MIT Energy Initiative for Science and Technology. Our intention in presenting these webinars is to share with you some of the ongoing activity in the low carbon energy centers and outside the low carbon energy centers as well. We want you to know what's going on at MIT broadly and what we think is important and interesting. And because we want to engage with you, we've decided to do this live. And so bear with us if we end up learning our technology in front of you as we proceed. We'd also like to hear from you in the course of the webinar and have reserved some time at the end to take your questions. I'd encourage you to type your questions onto the website where you'll find a little box that says type your questions anytime during the event, and we'll refer to them at the end. We'll also be recording the entire webinar in hopes that you'll refer to it if you'd like to take a closer look at the material later, and also share it with your colleagues who may not be able to attend. We're also very aware that because we have a global audience, many of our Asian members are unable to join us live. And for those who are, we apologize. And for those who see this in recording, we apologize too. We're going to try to do something about that next time, perhaps with more creative scheduling, or perhaps by even presenting webinars from Asia or other time zones. Let's see what happens. In today's webinar, we're going to hear from Professor Jacopo Buongiorno, who is the TEPCO Professor of Nuclear Science and Engineering and the Director of CANES, the Center for Advanced Nuclear Energy Systems. Professor Buongiorno's topic is nuclear power, and in particular, how this critical part of our energy system is evolving to adapt to the needs of base power in the 21st century. And so without taking up any more of your time, Jacopo, welcome and thank you.
Yeah,
It's all yours.
Thank you for having me, Rob. And so we're going to talk about new nuclear technologies, and in doing so, I'm going to leverage the findings from a recent study that we completed at MIT on the future prospects of nuclear energy. So let me get to the slides here so you can follow along. The cover of the study is shown here, and if you have an interest in nuclear beyond today's webinar, I would encourage you to download the report. The key messages are also listed on this slide. I'm not going to go over this, but 2 out of 4 of these key messages will be echoed in today's presentation. So before I jump into what these new nuclear technologies look like and what can they do for the energy infrastructure in the 21st century, let me just sort of give a very brief recap of where nuclear is today. So focusing on emission-free or carbon-free electricity generation worldwide, nuclear is a very big contributor there. You can see in places like the US and Europe is actually the largest generation technology of carbon emission electricity. In places like the Republic of Korea, the data are there because I gave a similar presentation over there recently. This fraction climbs up to almost 90%. Now, that's a snapshot of where nuclear is now. It is growing at good rates in China, India, Russia, and the Middle East. That means that there are ongoing construction projects for new nuclear power plants there, but it is declining in Western Europe, Japan, and the United States. Now, looking ahead, do we need, an important question is, do we need nuclear to deeply decarbonize the power sector? The emphasis here is on the word deeply. If one starts with a fairly high carbon intensity power grid, which relies heavily on coal, it is fairly straightforward to reduce carbon emissions somewhat. If one switches from coal to natural gas, emissions are reduced. Bringing a little bit of renewable capacity online also reduces emissions. But the emphasis here is on deep decarbonization. If we are to follow the recommendations of the climate scientists that want to decarbonize aggressively the power sector and the economy overall, then the power sector has to decarbonize very, very deeply and aggressively between now and 2050. So in the study that I mentioned earlier, we found a fairly compelling economic argument in favor of keeping and growing the nuclear share of the power sector. The punchline of that analysis is that excluding nuclear energy, which is carbon-free and dispatchable, from low-carbon scenarios can drive up the average cost of electricity. Now, let me walk you through the graph that you see here. At MIT, we have developed and validated a tool, it's called GenX, that simulates the optimal generation mix in power markets. The way it works is you pick a region of the world that you're interested in, and for that region, you need as input the hourly electricity demand, the hourly weather patterns, because that determines how much solar and wind you can get at any given time, the capital, operation, and maintenance fuel costs of power plants, including backup and storage, which you might need if you have a lot of solar and wind in your system, and finally ramp-up rates. How quickly can a power generation asset or power plant change its output to basically follow the load? It takes all that information as input, and it basically produces a generation mix which minimizes the average cost of electricity in that region. So the figure of merit here is average generation cost in dollars per megawatt hour. You can run that tool for different scenarios. A scenario might for example, exclude nuclear from being part of the scenario, from being part of the mix. Another scenario might have nuclear at a nominal cost. A third scenario might have nuclear at low cost. And you can make any assumptions that you want about the technologies that participate in the analysis or not. You can also run these different scenarios for different decarbonization targets. So the last variable that you should pay attention to in this plot is the x-axis, which is basically carbon emissions, CO2 emissions in grams of CO2 emitted per unit electricity generated. So grams of CO2 per kilowatt hour. So now focus on the results there. This particular region that I'm showing here is the Tianjin, Beijing, Tangjiang, is one of the most populous provinces or areas in mainland China. It has fairly expensive natural gas. It has fairly unfavorable renewables because of the high latitude. And you can see here that even at fairly modest decarbonization targets of the order of 100 grams of CO2 per kilowatt hour or 50 grams of CO2 per kilowatt hour, scenarios that do not include nuclear, so orange and blue, tend to have an average generation cost that is significantly higher than scenarios that include nuclear. And that cost differential increases as you drive down your allowable sort of CO2 budget. So you may wonder, why is that happening? And the answer is on the plot on the right. What it's now shown here is for the same region of China, the total installed capacity of all assets on that grid. And these scenarios are the scenarios excluding nuclear. So what you see here is that the total installed capacity, when you exclude nuclear and you try to drive down your carbon intensity, increases exponentially. And it's really that aggregate capacity, which is mostly solar, wind, and the battery storage that goes with it to manage the intermittency and meet demand at any given hour throughout the year, that really drives up the cost. So our analysis, which at this point has been repeated with different tools and different assumptions by other groups, not just at MIT, but worldwide, shows that in many important regions of the world, having a carbon-free, dispatchable, or controllable energy source is important if you try to decarbonize and keep the cost, your average cost of electricity low. So with that, we think that new nuclear power plants, therefore, should be built and be part of the future generation mix in the power sector. But what about cost? We've all heard that in the West, in the US and Western Europe, some construction projects for new nuclear power plants have been very expensive, and that's certainly a correct statement. What is shown in this plot here is the overnight construction cost. Now it's dollars per kilowatt, so it's per installed capacity. And it shows that for a set of either recently completed, proposed, or under construction nuclear power plants. And you can basically see that there are two groups here. Let me move through the animation. The first group is the Asian projects. And in Asia, whether it's South Korea or China or even Japan before they had the accident 10 years ago, or the Emirates, the overnight construction cost for new nuclear power plants has been quite reasonable, of the order of $3,000 to $5,000 per kilowatt. On the other end, if you look at the second group, which is essentially the US and Western Europe, you can see that the overnight construction cost is roughly a factor of 2. So in the study that I mentioned already a couple of times, we spend a lot of time and effort trying to understand why there is such a big difference in the construction cost and associated schedule delays between Asia and Europe. And one might initially think that this has to do with the difference in the technologies or the different reactor designs that are being built. But that's absolutely not correct. In fact, in all these instances, we're talking about large light water reactors, large meaning gigawatt scale. In some instances, we're talking about almost the exact design being built for example, in the US and in China. And you still see a big price or big cost differential. So in digging deeper on this particular topic, we ended up interviewing managers for construction sites in Asia, in the US, in Western Europe, and read the literature about mega projects and follow sort of the news releases about the progress of these different programs. And we basically learned the following, that there is a set of attributes for projects in Asia that have not been reproduced in the US and Western Europe. And we think that that's the main reason for the cost differences that you see here. For example, in Asia, they do not start to break ground on a new construction site until at least 95% in some instances of the detailed design of the plant is completed. By contrast, in the US and Western Europe, some of these plants or some of these construction projects that have gone disastrously wrong and have experienced big cost overruns have started with less than 50% design completed. So essentially the companies rushed into building the plant without having truly completed the design. There were some commercial and some government-related incentives that made this, that caused this, but that's really sort of the bottom line, is that they started building without a detailed design completed. The second point is that the companies in Asia and those countries in Asia have been building nuclear power plants continuously for the past 20, 30 years, and so they have supply chain and a workforce which are fairly mature and skilled. By contrast, because in the US and Western Europe, nuclear plants had not been built for a period of at minimum 20, in some instances 30 years, the supply chain is certainly not as mature as it is in Asia, and the workforce inexperienced. And there are many instances in which, at the specific projects that we are discussing here, components did not arrive on time, or they were not up to nuclear quality and things of that type. A third lesson that we learned, or a third item that we sort of extracted out of our analysis of these different projects, is that in the Asian projects, fabricators and constructors are included in the design team from the early stages of the project, and that ensures that whatever design is developed is constructible. Whereas in the US and Western Europe, that's not been the practice. We also found some important differences in the way the contracts were set up and the composition of the team. There are some aggravating factors for that further explain or amplify the differences between the Western projects and the Asian projects. The first is the productivity of the construction sector, not just for nuclear construction projects, but for construction in general. In the US in particular, and in the West in general, the productivity of the construction sector has been declining since the 1960s. That's surprising, but that's the fact. By contrast, other sectors of the economy, for example, manufacturing or agriculture, have seen their productivity increase quite rapidly over the decades. The potential implication of this for new nuclear is that you may want to shift more and more scope and labor from inefficient, non-productive construction sites to very productive and efficient environments such as factories and shipyards. But we'll talk a little bit more about that later on. The second aggravating factor for the differences that we see between Asia and the West is the wages and labor rates. Not surprisingly, in places like China, but even Korea, both for construction and engineering crafts, the wages tend to be significantly lower than in places like the US, the UK, and France. In our study, we took a sort of a reference plant for which we had data in terms of the number of hours required to build or to construct the different parts of the plant. And when you roll up and you multiply those hours times basically the labor rates, and when you roll up this data, we found that the difference between China and the US in terms of overnight construction cost for China would be of the order of $900 per kilowatt, and for Korea about roughly half of that. So these are significant numbers. They don't explain the factor of two difference that I showed in the previous slides, but they are, as I said, aggravating factors. So where do we go from here? If the West has lost its know-how to build nuclear power plants, well, there might be a role for advanced reactors in ways that I will explain now. Again, in our study, we looked at the way that the nuclear industry does innovation, and we compare that to the way in which other important industries of our economy do innovation. And you can see here on the table the industries that we analyzed, again, through interviews and literature examination. Nuclear plants, coal plants, offshore oil and gas, chemical plants, satellites, jet engines, pharmaceuticals, automobiles, consumer robotics. So you see it's a broad range of industries, not just energy and not just heavy industry. For each of these industries, we wanted to analyze four categories. First, the size of the system, or the machine, if you will, that is at the heart of that industry. So for nuclear plants, traditionally it has been a large light water gigawatt scale system, so it's massive. Nuclear is not unique in that sense. Chemical plants tend to be pretty large in physical size, same for coal plants, offshore oil and gas. At the other end of the spectrum, you might have consumer robotics or jet engines, automobiles, they tend to be a lot smaller. The second category is factory fabrication versus construction site. And again, here you have examples like nuclear, which traditionally have been built at construction sites, and you have examples of products and systems that are routinely built in high productivity facilities such as factories. Examples like satellites, jet engines, of course, automobiles, etc. The third category is has to do with licensing, is licensing of a new technology within these industries, subject to a lengthy and costly safety-driven process. In the case of nuclear, the answer is certainly yes. Again, not unique. If you want to license a new or market a new medication, you need to go through a very, very lengthy testing and licensing process, the same for automobiles, the same for jet engines, and so on. And lastly, is the product that this industry produces. It's a high return or it's a commodity. In the case of nuclear, traditionally has been electrons sold to an interconnected grid, which is obviously a commodity. In other instances, in other cases, for example, pharmaceuticals, automobiles, consumer robotics, there is certainly a premium associated with product, and they're not commodities. So you see that nuclear is not unique in any one category, but is the only industry that has negative attributes in all four categories. So I call this the perfect storm of unfortunate attributes. And the bottom line is that this has resulted in a very long, order of 20 years, and costly, order of $10 billion, innovation cycle for new nuclear technology. Just to be clear, what I mean here by new nuclear technology, I mean a new nuclear reactor design. It typically takes 20 years and $10 billion. Now, I don't need to explain that in today's environment, this time scale and this magnitude of investment are completely unacceptable. And so if this industry in places like the US and Western Europe is to have a future, the paradigm by which they develop, demonstrate, and deploy innovative nuclear systems has to shift radically. So first of all, it has to go to a more smaller, physically smaller, serial manufactured systems. I will explain what I mean by all of this in the upcoming slides. The testing and licensing has to be much accelerated with respect to the past. And lastly, I believe that the energy products that are produced by nuclear systems have to have some higher added value than just sort of electrons pumped on an interconnected grid. Okay, so let me now examine each of these sort of propositions one at a time. The first is smaller systems. I think the industry is getting this. There is a clear push in the US and Western Europe towards smaller reactors. An example is shown here. This is the GE General Electric BWRX 300, which is shown all the way to the right. And it's compared to the previous generation GE product that was called the ESBWR. That's a 1.6 gigawatt scale reactor as compared to BWRX 300, which is 300 megawatt reactor. So not only the power output is lower, but in terms of physical size, as you can see in this graphic, the volume is reduced by 90%. What's of course more important is what is the reduction per unit of electricity generated, and there is over 50% reduction in building volume. Construction of building in a nuclear power plant costs a lot, and over 50% lower concrete. At the same time, we're still talking about the same technology. So there is not a radical change in the materials that are used, in the fuel types that are used. The components still look more or less the same. They're shrunk down. There is a lot of simplification for sure in terms of elimination of components. But the target overnight construction cost for these systems, and I emphasize that's a target because it has not been demonstrated yet, it's of the order of $2,500 to $3,000 per kilowatt, with a levelized cost of electricity of the order of $50 per megawatt hour or less. So needless to say, at that level, if they can prove and demonstrate they can get that, then it would become competitive even without carbon taxes or anything like that against natural gas. At 300 or 200 megawatt, in that range, it's also an ideal size for replacing aging coal fire plant or natural gas fire plant when we decide to deeply decarbonize, and still being able to use existing infrastructure at the sites, things like cooling and switchyard, transmission lines, and so on could be reused. It can be deployed in smaller increments, and very, very importantly, the magnitude of the investment is now of the order of, say, $1 billion as opposed to $10 billion. So in terms of overall financial risk, it's lower. These systems are designed from the outset for frequent load following, again, recognizing that they have to operate in an environment where not just demand fluctuates, but also generation might fluctuate. They tend to be located physically below grade. This enhances physical security, for example, against airplane crashes. They're based on proven technologies I mentioned, and the good news, I guess, for the industry is that this push for small modular reactors is really led by Western suppliers, and so it also becomes an opportunity for the industry in the West to sort of regain the lead in nuclear technology. What these small modular reactor approaches do or might do, I should say, for cost is the following. The idea here is that you would deploy multiple units, standardized, each one is identical to the other, at the same site. This has shown to be an effective way to reduce cost even for larger nuclear power plants. When you build them in series, particularly at the same site, the cost of the latter units is lower than the cost of the earlier units. They also tend to use advanced concrete materials. Concrete is typically a big contributor to the overall cost of a new nuclear power plant. It requires some multi-step, labor-intensive process to erect a reinforced concrete structure. And there are now materials that have been used outside the nuclear industry that can be used for new nuclear reactors to basically reduce the amount of labor required for those structures. The modular construction itself, SMR stands for small modular reactor. The modularity here means both that you have identical small reactors, but it also means that large sections of the plant are now pre-assembled in factories and then transported to the site and connected, as opposed to being stick-built at the site itself. And lastly, also something that we recommend in our study is take a hard look at seismic isolation, because a lot of what becomes site-dependent for new nuclear power plants in the design is associated with the requirement, of course, to be able to withstand a large earthquake. And if you put your system or your plant on seismic isolators, those requirements are a lot less severe, and you can basically come up with a standardized design that will work everywhere. Okay, so with these innovations, it should be possible to, as I mentioned, shift labor from site to factories. That in turn should reduce the installation cost, standardize the design that reduces the licensing and engineering cost, maximizes learning, and finally short construction schedule, which reduces interest during construction. Now, there are several industries in which these approaches have been implemented, including an example in the nuclear industry. In Japan, the ABWR series of reactors had a large scope of modular construction and resulted in about 20% reduction in cost and schedule. But in other industries, it's been, in some instances, transformational, with a reduction in capital cost and schedule of the order of up to 50%, things like chemical plants and nuclear submarines even. Now, if you take this idea of smaller concept or smaller nuclear reactor to an extreme, you can actually arrive to what I've been calling a nuclear battery. It's shown here. The idea now is a very, very small nuclear fission reactor of the order of 1 to 20 megawatt. You can see the physical scale is such that this system would fit within a standard shipping container. It is coupled to a power conversion unit, either a Stirling engine or an air Brayton cycle. It features a block core made of steel or other compatible material with heat pipes, so there are no moving parts. So here the energy that is generated by fission in the core is actually removed by heat pipes, is taken to the power conversion unit, and that's where basically the electricity is made. It would be self-regulating. This has been actually demonstrated in similarly small reactors. It would be an entirely standardized design, built in a factory, put in a standard shipping container, arrive to the site, whatever the application it is. The idea is to have sort of plug-and-play operations, possibly autonomous or semi-autonomous operation, and no on-site refueling for 3 to 5 years. So once the reactor fuel runs out of juice, so to speak, the old battery, the nuclear battery, is basically shipped back to a centralized facility, and there is refueled. Examples of these nuclear batteries are the Westinghouse E-Vinci concept that is being developed by Westinghouse. It's been under development for a couple of years. That's less than 10 megawatts. You have Megapower. That's a project that originated at Los Alamos. Hollows Jan, it's a smaller company, and for niche application, space application, NASA has also developed a nuclear battery at less than 100 kilowatt. All these systems share an exceptionally robust safety profile, which, in my opinion, will be able to accelerate their testing and licensing dramatically. So let me just walk you through briefly here. In all these instances, you do not need, for all these designs, you do not need emergency AC power to cope with abnormal situations. So you don't need external energy sources to actuate or to drive your pumps or safety systems and so on. The system does not basically need any external intervention, either by the operator or by engineer systems. It is very, very simple. I mentioned no moving parts, fewer components, so they tend to be very simplified design, and also that simplifies operations, the number of things that people have to pay attention to during operation. And last but not least, because of the fuel forms and the way in which the system responds to an abnormal event, the emergency planning zone, essentially the zone that could be affected during an accident, is limited to site boundary. So there would be no need in that case for any sort of evacuation or routine training of the local population. So these attributes have been not only demonstrated but also been put to good use in the demonstration of one of the concepts that I mentioned in the previous slide. So this is an image here that you see of the kilopower. Actually, it's called Krusty. It's sort of a prototype of kilopower that NASA has been able to design, fabricate, and test between 2015 and 2018, so less than 3 years, and at a total cost of less than $20 million. Now, again, this had different requirements. It was for space applications, but in fact, in terms of design overall philosophy and safety profile, very, very similar to the concepts or the systems that are being developed for civilian applications. So if you compare now these numbers to the numbers that I gave you earlier for traditional demonstration of new nuclear reactors, you see that you're basically saving about a decade and early $1 billion. So that's why there is a lot of excitement about these nuclear batteries now. The third item is, how do I add value? How do I decommoditize energy products that are produced by nuclear systems? Now, there are two ways of doing that. The first is, frankly, completely out of our control. A strong policy from governments, policymakers that recognize the non-emitting nature of nuclear electricity, the fact that it has a positive impact on local economy, contribution to energy security, et cetera, et cetera. Of course, that would add value to electrons on the grid, electrons generated by nuclear plants. The other way is to basically capture new markets in which your product is not a commodity, but is valued with a higher value. And so this could be heat, hydrogen, production of synthetic fuels, water desalination, maybe remote communities, mining operations, propulsion. In many such applications, you're now competing against expensive and polluting fossil fuels like diesel fuel, diesel generators. And so it becomes a little bit easier to show the value of your product. So I'm going to now go over, this is the last part of the presentation, I'm going to go over several such applications in which I believe that these nuclear batteries in particular can provide value that is needed and desirable. So the premise of this is that it's not all about the power grid and it's not all about electricity. In fact, if you look at the total carbon emissions worldwide, only about 1/4 are associated with electricity production. About the other 3/4 are in sectors like transportation, industry, buildings, and agriculture. So if we're serious about decarbonizing the global economy, we need to tackle not just the power grid, but we need to tackle all these different sectors. So heat could be a very, very big market. Many industries that use processes to produce materials or chemicals require heat. They require heat at different temperatures. And depending on that temperature, you can use a nuclear reactor, you can use other technologies. The technologies that we analyzed in our study here are shown here. So you could, in principle, even use solar PV. You get electricity, you turn it into heat. Of course, it's not very efficient thermodynamically, but it's possible. Or you could use solar thermal tower with storage. You could do the same trick with wind, get the electricity and turn it into heat. You could use nuclear or you can use natural gas. And right now in the US, we're using natural gas because it's the lowest cost. And if there is not a carbon constraint, you would probably continue to use natural gas. But if you take natural gas out because we dislike the carbon, CO2 that is pumped into the atmosphere, when you burn it, then you're left with the other options. And so the first column here shows the levelized cost of heat. So now it's dollars per megawatt hour thermal for the different technologies. The second column says, okay, is this a dispatchable energy source or it's intermittent? And the third is low carbon. Now, industries, factories do need dispatchable heat. They need the heat when they need it, not randomly. So let's look at cost. You may be surprised to see how low the cost of nuclear is, but remember that the thermodynamic efficiency for a nuclear reactor is of the order of 33%. So if the cost of electricity is $100 per megawatt hour coming out of a reactor, the cost of heat generated by that reactor is 1/3 of that, and that's why you see the range there. And so if you compare that to the other options that you have there, it's quite competitive. It's also, of course, dispatchable, and it is low carbon. So in my opinion, it is possible that we'll see in a carbon-constrained industry the use of nuclear heat for a lot of applications. We went a little bit deeper on this, and we look at the U.S. Market in particular. So we went to the EPA database, which reports all industrial sites in the United States emitting 25,000 tons of CO2 per year or more. We only consider sites that need at least 150 megawatt of heat, so the ones that require a lot of heat, basically. We assume that nuclear heat can be delivered at a maximum of 650 degrees C. This is possible with current technologies called the high-temperature gas reactor, or even one such nuclear battery can do it. And we consider all sorts of chemicals and other materials and processes that could accept that heat. And when you run these filters through the EPA database, we came to the conclusion that now you could basically replace 150,000 gigawatt equivalent of natural gas with nuclear heat in the United States. And that alone would displace of the order of 240 million metric tons of CO2 equivalent per year, which is about 7% of total annual greenhouse gas emissions. So that would be a very good contribution, and it would be obviously also a large business opportunity for nuclear. The other sector that we looked at, sort of top-down, big picture, is transportation. So in the transportation sector, you can either electrify, so go from internal combustion engine to electric vehicles, or you can go with fuel cell vehicles. In that case, you need hydrogen. In the first case, obviously, you just need electricity. So the numbers, the assumptions under which these numbers have been generated are shown at the bottom of the slide. And they tend to be sort of upper end estimates here. But the idea here is pick the US and say you go with electrification. So our estimate suggests that if the US entire transportation sector, which means cars, trucks, trains in particular, were to convert to were electrified, you would need of the order of 280 gigawatt of new electricity. And that's an enormous number. And of course, part of it could be provided by nuclear. And then you see the numbers, of course, scale in different countries according to the size of their transportation sector. For the world, is about 1,000 gigawatt. Now, if you do it with hydrogen, and here we made the assumption that hydrogen would be produced with high temperature electrolysis. So you need both heat to raise the temperature of water before you crack it, and then electricity in the electrolyzer to crack. H2O and O2. And in this case, the numbers become even bigger. So again, big business opportunities. So there are also applications that don't fall under transportation or industry. And one such application would be agriculture. Another one it could be production of medicines and so on. So the very last part of the presentation here focuses on what I've been calling collocated supply and demand. What is meant by this here is physical collocation of energy generators, like a nuclear battery, and the end users, the demand, the application that this energy is used for. So if you think about in history, collocated supply and demand has always been used, and it's always been, why? Because it's always been the most efficient approach. You can go back to the pre-industrial revolution times, water mills for production of flour and olive oil. Of course, that's an example of collocated supply and demand. But even closer to modern days, at the start of the industrial revolution, was the collocation of hydroelectricity with textile factories, and we have some examples here in Massachusetts of towns that really were born out of that collocation. Now, in the 21st century, collocated supply and demand could look very different. It could be now the supply, it would be basically a nuclear, or could be a nuclear battery of the type that I've shown a minute ago. And the demand could be a number of production and processing technologies that are off the grid, mobile, containerized, but not necessarily mobile and containerized. Things like containerized agriculture or aquaculture or pharmaceuticals, 3D printing, data centers. I'm going to walk you through some of these applications in the remaining slides. In all this, for all these applications, the technology or the system is high capital intensive, which means that you want to run it with a stable output or a stable input of energy all the time. So that's the first column of the table there. You need an energy source that is stable in time. You want it carbon-free for obvious environmental reasons. You probably want it geographically constrained because a lot of these applications are all over the place. Perhaps suitable for mobile deployment in some cases, not always, and then with a predictable generation cost. And so I went through basically what the options are. You have nuclear traditional, say a large nuclear power plant, or nuclear batteries, the type that we discussed, natural gas, coal, hydro, solar, and wind. And in my opinion, if you run through these 5 categories here, the only technology that can really check all the boxes positively is the nuclear battery. So I would submit that it is almost like the ideal energy source for a lot of these applications. Let me walk you through briefly some of these co-located supply and demand applications. The first is agriculture. So there are several products like freight farms and Growlaner and so on by Philips that you can go online and find out about. And essentially what they are standard shipping container, that's the size, within which you create a controlled environment, controlled in terms of temperature, light, and humidity. And you can grow whatever you want. And now, obviously you wouldn't grow commodity produce that you can grow much more efficiently in fields. But if you start with high margin produce, like we look at romaine hearts, saffron, or abalone, which of course is not a plant, morel, and truffles, then the ability to produce them in this containerized mini farms actually is economically quite attractive over a broad range of electricity costs. And all that is required really in this case is electricity. Aquaculture, the picture shown here is from the Emirates. The Emirates are now not self-sufficient, but close to being self-sufficient in terms of fresh salmon production. They don't import it; they actually produce it in their own country. And if you think about the Emirates, the last fish that you think would be able to thrive in the Emirates is salmon. But obviously, it's done indoor and in a facility that has a control environment, in this case, in terms of temperature, and it requires electricity for water circulation and filtration. It's a nascent market, and on land, of course, aquaculture is established along coast, but there the need for electricity is not as obvious. Number 3, production of pharmaceuticals. Local production of pharmaceuticals. GE offers a product. It's called Q-Bio. It's essentially a modular factory for producing things like synthetic insulin or medicine for cancer treatment and rheumatoid arthritis, among others. And as a mini factory, it requires electricity for lighting, heating, ventilation, and air conditioning, for the clean room, utility equipment, and fluid pumping. It is a nascent market. Advanced manufacturing, again, GE here, the M-Line or the Autodesk, that's a different manufacturer. Mini factories that you can put next to customers, and they basically have 3D printers, large 3D printers, and they can produce high added value components for industry. Once again, they require electricity for large 3D printing machines, and for the instrumentation and control, they obviously require also raw materials for the components. Water desalination is a total no-brainer in the reverse osmosis version of it. It's highly modularized, and it does require just electricity. If you want to go for a higher efficiency process, then you're probably going to need a combination of electricity and heat, again, something that a nuclear battery would be able to give you. Currently, the market for desalinated water worldwide is fairly small, 16 gigawatt equivalent, but it's growing very rapidly, and for some countries, it is actually the only source of fresh water that they can have. Data centers is another one. They tend to become bigger and bigger and require more and more power. In some cases, they are even modularized and containerized, as you see here on the bottom left. In some cases, are remote. So again, the cost of transmission and connecting it to a grid might be high. You put a nuclear battery locally, and you can serve the needs. This is a real interesting process that has been developed by the Office for Naval Research for synthetic fuels. It is literally electricity plus seawater equal diesel fuel or jet fuel, whatever other hydrocarbon you want. Sounds like magic, but it's not. There is CO2 dissolved in seawater. This process, which is an electrochemical electrocatalytic process. Essentially removes CO2, separates CO2 from water, then it cracks water, it combines hydrogen with CO2, and then through a Fischer-Tropsch process you get whatever hydrocarbon you want. It's interesting that about 60 to 80% of the electricity input, which is the only energy input that you require, it actually shows up as energy content of the final fuel. So it tends to be quite efficient. Cost-wise, it's there are some estimates about maybe $6 per gallon of diesel. So it's not obviously directly competitive with fossil-based fuel, but in a carbon-constrained world and for some applications, they might be interesting. Shipping and onboard manufacturing, about 90% of international trade is by sea. These nuclear batteries could be used for propulsion. These would not be very different from what is already done in nuclear submarines and aircraft carriers by some navies. But you can go even a step further. You can have entire production lines on board, load the raw materials at the departure port, then basically make your products en route, and then deliver the finished products at the arrival port. And what's required there is electricity for the production lines, for HVAC, and for the 3D printers, whatever it is you're using there. So that could serve as well. The last application that I'm going to mention is offshore hubs. Again, a little visionary here, but there are already some offshore facilities that require a lot of power, and they currently burn natural gas to get that power. For example, oil and gas rigs. Or even some airstrips that are located offshore. And in the future, we could also envision that there will be entire residential areas or maybe some industrial areas that will be somewhat offshore. And again, this would couple quite well with nuclear batteries. So the bottom line is that nuclear, of course, is an important contributor of the energy infrastructure now. The present looks like what you see there above. It's very large gigawatt scale reactors. Maybe the future will look very different for nuclear. So there is, as I mentioned, a lot of interest in small modular reactors and nuclear batteries. The drawing that you see here at the bottom is our own rendering of what a site with nuclear batteries might look like. And the battery you don't actually see there, it would be below grade. The parallel pipe, those sort of boxes that you see there are basically the power conversion unit and then the transformer. So maybe that's what the future will look like, and we shall see. So with that, I'll stop, and I am very happy to get any questions that you might have.
Okay, very good. Thank you.
Good. Thank you.
Thank you from our studio audience. Jacopo, you remind us that replacing 100 quads of energy consumption a year in the world is a big task. And you can get part of the way there with solar panels and windmills and batteries and perhaps other things, but it's an enormous amount of energy, and it's not all in the electricity system. It's all over the place.
Correct.
And you've presented us with a vision for making reactors differently that makes them small enough and potentially portable to be used in a very wide range of applications, which is exciting. But we're still sort of confronted with the problem that nuclear power has confronted for years, which is public acceptance, concerns about security, concerns about what happens to spent fuel when it needs to go back somewhere. How are those things handled here, and are you convinced that we can really get to a sort of ubiquitous nuclear world?
So first, let's start with some technical information there. None of the systems that I presented today really give you any dramatic reduction in the amount of spent fuel or waste that would be generated. So depending on the fuel form, depending on other technical characteristics of the reactor itself, you may be 20, 30% lower generation of waste per unit energy generated. So it's not a game changer in that sense. At the same time, I would submit that the waste problem is sort of grossly overestimated. It has been very, very difficult not to crack from a political point of view. The process leading to identification and licensing of a nuclear waste repository in countries like the US certainly has been very, very complicated, and we're not there yet. And I personally think that the current plan, which is to store these waste at the site in Yakima, is just politically unfeasible, and so the U.S. should look for alternatives. There are also positive examples of this, though, in the world. The two countries that are probably going to get to the finish line of opening a repository for nuclear spent fuel are Finland and Sweden. They've done it very differently than the U.S. They've done a consent-based process. They've actually asked communities who was interested to take the repository. They had several bids, and through a more rational process, they were able to get to a repository. The other point I need to make about waste is that the volumes of materials that generated tend to be very, very small. People maybe don't appreciate this, but if a person like you and me used only nuclear electricity throughout our lifetime, the amount of nuclear waste or spent fuel that we would generate would be about 1/10 of this cup. Mm-hmm. That's it. That's total, mm-hmm. Right? So
it's not going to be going up and down the highways.
Yeah, right. I mean, it's small overall, and from a technical point of view, there have never been major impediments. The current practice in the U.S. is to store it in dry casks. So these are cylindrical canisters that are made of steel and concrete. And they're safe, cheap, easy to handle. They can probably last 100 years, maybe even longer, or they can be, the fuel can be put in new dry cask if they degrade. But ultimately, you need a repository, mm-hmm. And so this goes back to my earlier.
And it sounds like possibly co-located with the facilities where these, say, batteries are recharged or refueled.
Exactly, where they're recharged, not necessarily where they are used, where they're right. Applied, right? The whole idea of a battery is that once you're sort of run out of energy, you dispose it. In this case, you would send it back to a centralized facility where it's refueled. And so then that centralized facility would handle basically the spent mm-hmm. fuel. But the question still remains: is what are they going to do with that material? And so right. ultimately, you do need a repository.
I guess another big question is this really getting us there in decarbonization? I mean, is the life cycle CO2 produced? And this is I'm riffing on a question that's come in from the audience, and keep them coming, please. Right. Is the amount of CO2 that's produced over the life cycle of a plant, which may be many, many years, going to be low enough to move the needle? Can you really get it down to something like 1 gram per kilowatt hour?
Well, I don't want to mention a number because I don't have them sort of fresh in my head, but there have been several life cycle studies of CO2 emissions associated with the different energy technologies. And in all these studies, nuclear in its different versions, typical traditional versions, is the lowest. So, mm-hmm. I mean, you really get, what you have to appreciate is that the amount of energy that you get out of the nuclear fuel is absolutely enormous. It's about pound for pound, like 100 million times more than, or more like, or millions of times higher than say coal, natural gas. So there is no doubt that it's a good way to reduce CO2 emissions, but it boils down to which sectors of the economy are going to use it, right? So as per my presentation, 25% of emissions are in electricity. So fine, let's try to decarbonize the grid. But then what about the other 75%? And I think that's where these batteries can probably move the needle in some of these other sectors which seem to be so difficult to decarbonize.
Yeah. Nuclear is a heat source. It's interesting to have.
As a heat source, or even electricity but off grid, right? So mm-hmm. microgrids are directly to the co-located supply and demand, as I call it, which really means your electricity goes straight to the user. It's not circulated on an interconnected grid.
Actually, before we leave the topic of CO2 emissions, I wonder if you don't want to cite numbers on air, yeah. So to speak. Is there a reference where we could send audience members who are interested in looking at these things?
We certainly can. I can think of 2 studies that I've examined in the past, and that's where I'm, from which I'm drawing my statement that the life cycle of CO2 emissions is very, very favorable for nuclear. And now, I don't think there has been a study done for this particular design for the mm-hmm. batteries, but I would be surprised if it's any different than the past. Yeah. So I'm happy to, of course, dig a little bit and find out the information.
So maybe we make those available on the site.
For sure.
I was trying to picture a factory where these systems are made, sort of looking like a satellite factory, so to speak. And my sense from your table was that a satellite has many of the attributes that these nuclear batteries would have. They have high regulatory requirements, but they can be made in a factory, et cetera. But how thoroughly can they really be tested in a factory? Can you actually put a critical fuel bundle in one, or is that something that's going to happen out in the field?
Good question. So first, let me say the analogy that I like better even than satellites is jet engines. They are about the same physical size. In terms of technical complexity, jet engines might actually be more complicated than these machines.
So same question. I mean, they're not testing them for the first time when they're hanging from the wing of an aircraft.
Right. Exactly. No, they're not tested. There are two levels of testing, so to speak. The first is you first need to sort of demonstrate the technology. That's part of the licensing process for the Nuclear Regulatory Commission, say, in the U.S. That would be done at like a Department of Energy site. It could be the Idaho National Lab. Just an example that everybody's familiar with. And in that case, the first time you test it, of course, you need to build in some big margins because you don't know exactly how the system is going to behave. You put it through a testing program through certain transients and postulated and forced abnormal situations, and then you just see how it responds. Those tests are going to be very important because they allow you to validate your codes and your modeling tools that then you're going to use for subsequent design development and things of that type. But to your point, in factories you can certainly fuel
You can, okay.
You can, and you can do basically zero power testing to see that all systems are functional, even in a factory. It would have to be licensed as a nuclear facility at that point, okay? But it would not be a nuclear power plant. So when I say zero power, because of the physics of fission reactors, you can basically convince yourself and assure that the system is working without generating any power. The implication of this in terms of safety or radiological implication for the factory is that a zero power means that basically there is no real fission is taking place, not a lot of fissions, and therefore you're not generating a lot of radioactivity. So that keeps it. I don't know if that answers.
Yeah,
your
I think so.
So I think there are ways to basically test them before you send them in the field. Yeah.
Okay. We're running out of time, but perhaps just one last question about conventional nuclear reactors and the difficulty that we face in manufacturing these things in the field, and beginning with incomplete designs and so on. And I think that's a very important aspect of this cost differential that we see in different parts of the world. But it did make me think about the possibility of using emerging technologies like 3D printing of concrete, for example, to make these sorts of plants.
Yeah, we've been looking at it. And I mentioned that in one of the slides, particularly for the small modular reactors, people are thinking not only to prefabricate larger systems, say in a factory, and then transport it to the site and then sort of chain it, link it together, but also how do you streamline the construction of some structures will have to be built at the site, right? Because they're too big, you can't just transport them. And so in that context, I think there is interest and the companies are looking at, can I use 3D printing of concrete? And just to be clear, 3D printing of concrete, it's not the same as 3D printing of
it's a big machine.
It's a big machine, right? That basically just has an arm and goes and pours the concrete where it's needed. So that's one, I think, one technology that people are paying attention to. The other one is using high-strength rebar. It reduces basically the density of the rebar cage, which is so labor-intensive to put together. It also creates some issues related to voids generated or voids created within the concrete, and then you have to sort of vibrate and make sure those voids go away. So if you have a less dense rebar cage, that helps big time. There are also concrete technologies that eliminate rebar altogether. And I didn't mention this, but in our study we have found that really what costs so much about reinforced concrete, traditional style, in nuclear plants is the steel. Is not just the raw material, but it's everything associated with the steel. The rebar, and then the pouring and the formwork and all that kind of stuff. So there are some concrete materials that basically do not have reinforcement, but it's not in the form of a steel rebar. It's in the form of almost like fibers. of steel that are dispersed within the concrete cell. So yeah, it's a very good question. And what's interesting, last thing I'm going to say is a lot of these solutions or a lot of these technologies have already been not just tested but demonstrated really in civilian infrastructure, even in the United States. And so it becomes simply a matter of bringing them into the nuclear world, so to speak. So that means code standards and so on have to adapt.
It all takes time. Well, I'd like to thank you for the time you've given us.
Pleasure.
This was fun. I
you.
learned a lot. I hope you did too. If you've enjoyed this webinar, perhaps you'll come to our next one, which will be in late March, and it will be on mobility of the future and findings from our recently published study on the mobility by the Mobility of the Future team, and it will be led by Randy Field from Mighty. So we look forward to seeing you then, and thank you again.
Yeah, have a great day.
Cheers.